Hello and welcome to the last part of this lecture on dynamic charges. In the previous lecture, we were discussing the Liénard-Wiechert potentials. We had obtained the Liénard-Wiechert potentials by considering a point charge which is moving along a certain trajectory. And now we are going to find out, we're going to apply this Liénard-Wiechert potentials and find out the actual electric and magnetic fields. Okay, so these are the Liénard-Wiechert potentials. We got phi and we got A. We see that A, if we know phi, we can find out A, provided we know the velocity, of course. We should know the velocity if you want to find out phi. So that means, in other words, if we know phi, then we can automatically find out what is A. So now let us say I want to find out a charge which is being accelerated, which undergoes some kind of an acceleration in some arbitrary acceleration. Then I want to find out what are the electric and magnetic fields. Now we already know from our lecture on gauge invariance, electric field is given as minus grad phi minus dou A by dou t, and magnetic field is given as curl of A. So now all we have to do is we need to find out the gradient of phi. We have to find out the time derivative of A, and then we have to find out the curl of A. And once we get these three quantities, we need to combine them in this way, and that is going to give us electric and magnetic fields. Now that is easier said than done, because as we will see in the remaining part of the lecture, it's actually quite involved. Just to obtain this gradient of phi itself is actually a very tedious process. So let us, it's actually gives you, even though the calculations, the computations are quite tedious, but actually it gives you a lot of insight into what goes on when you are considering an accelerated charge, and you apply the concept of retardation, the retarded potentials, to an accelerated charge. So let us first find out the electric field. Okay, we are ultimately interested in finding electric and magnetic fields. So let us first find out the electric fields. Electric field is minus grad phi minus dou A by dou t. So we'll first start, and we have phi and A, which is given like this. So we'll first start with finding out the gradient of we need to find out the gradient of the scalar potential. So gradient of scalar potential, so scalar potential is this. Gradient of scalar potential, qc by 4 pi epsilon naught, they are constant, so they will come outside. So you'll have to apply the gradient on this quantity which is in the denominator, that is rc minus r dot v to the power minus 1. We have to find out the gradient of this quantity. Now finding the gradient, again we have to use, because we are having something to the power minus 1, so we'll have to use the chain rule here, and when we apply the chain rule, then we get this gradient of this quantity is equal to minus 1 by rc minus r dot v square times the gradient of rc minus r dot v. So this is what we have, and we apply the gradient individually on these two terms. So we have this, and of course we incorporate the minus sign here, so this minus and this minus, this will become plus. So we first have gradient of r dot v minus c into gradient of r. So let's call this as equation number 1. So we need to now evaluate these two terms separately, the gradient of r dot v minus c into gradient of r. So these two terms we evaluate separately, put them back together, that is going to give us the gradient of phi. Now before we proceed to find the gradient of r dot v, let's just have a look at the second term once. We know that the retarded time is defined as tr is equal to t minus r by c. So from here we just rearrange this, we get r is equal to c into t minus tr. So if that is the case, then the gradient of r, you take the gradient on both sides, gradient of r will be equal to minus c into gradient of tr, because gradient of time will be 0. So gradient of time is 0, so minus c into gradient of tr, that is going to be your gradient of r. So gradient of r is equal to minus c into gradient of tr. But we will not find the gradient of tr, the retarded time, right now. The reason is this quantity, as we will see later, the gradient of r dot v, that will also provide us terms, and those terms will contain individually. Okay, this is going to give us 4 different terms. When we expand this using a product rule, we'll get 4 different terms, and each of these 4 different terms, when we simplify, we'll find that each of these terms will also contain this gradient of tr. So we would like to first evaluate this one, and then we'll collect all the gradient TR terms, and then we will subsequently evaluate what is this gradient of TR. So right now we'll just leave gradient of RS minus C into gradient of TR. We'll call this as equation number 2. So now to evaluate the first term, that is gradient of R dot V, we use a product rule. Okay, so this product rule, it is there in Griffith's chapter 1. You could just have a look at it once. So it basically says that gradient of the dot product of any two vector fields, gradient of the dot product of any two vector fields will give us 4 different terms. The first term will be a dot product term, the first and second terms will be dot product term, and the third and fourth terms will be cross product terms. So this is how this term is going to pan out. So now it's just a matter of just substituting here. So what we do is, we, instead of x is equal to r and y equal to v, we just substitute that. So x equal to r and y equal to v. So this is going to give us, this term is going to give us r dot del into v. This term is going to give us v dot del into r. This term is going to give us r cross curl of v, and this term is going to give us v cross curl of r. Let's call this equation number 3. So now we have the first term, it led us to 4 different terms. Now we will evaluate each of these terms. We'll just evaluate each of these terms one by one. So let's consider the first term. Okay, the first term, that is r dot del into v. So how do we get this r dot del into v? So r dot del, the only way we such kind of terms, whenever we face such kind of terms, the only way we can work them out is by just expanding it. So r dot del, okay, so r is equal to rx I cap plus ry j cap plus rz k cap, and del is nothing but dou by dou x I cap plus dou y j cap plus dou by dou z k cap. And when I take the dot product of these two, r dot del, it's not exactly a dot product because the nabla operator, it is not a vector. Okay, it's like a vector, but it's not exactly a vector. But still, when we take the inner product of r and del, so we'll get rx dou by dou x plus ry dou by dou y plus rz dou by dou z. So now this is then operator. Now this operator will operate on the vector v, which is a function of tr. So when we apply this one on this, so we'll get rx dou v by dou tr. Rx into dou v by dou x. Now v is explicitly it's a function of tr, and tr depends on r, so that means we'll have to apply the chain rule on this. So dou v by dou x, we'll have to apply the chain rule. So first we have to differentiate v with respect to tr, then we have to differentiate tr with respect to x. So dou v by dou x is equal to dou v by dou r dv by dtr, because v depends only on tr, so it will become a total derivative. So dou v by dou x is equal to dv by dtr times dou tr by dou x. Same things happens for the other two terms as well. Now you can notice here we have dv by dtr, dv by dtr and dv by dtr. This is the derivative of velocity of the charged particle as it moves along its path. So derivative of velocity is nothing but the acceleration. So we can take these 3 terms, this acceleration term, we can just take it outside, and then what is left behind is rx dou tr by dou x. So here this is x, the x component of r, y component of r, z component of r. What is this? This is the x component of gradient tr, right? And this is the y component of gradient tr, and this is the z component of gradient tr. So what are we having? X component of r multiplied with gradient x component of gradient tr, y component of r is multiplied with y component of gradient tr, and the z component of r is multiplied with the z component of the gradient of tr. So in other words, what are we doing is we are doing a dot product of r with the gradient of tr. Okay, so this remaining terms, when we take this dv by dtr common outside, what is left behind is r dot gradient of tr. So that will be the first term. Now moving on to the second term. So we have v dot del into r. So we want to evaluate this. So v dot del equal into r. Now if we remember, r is nothing but small r minus W. Okay, small r is the field position, and W is the position of the particle. So this is the separation vector. So capital R is equal to small r minus W. So I just substitute here. So we have V dot del capital R is equal to V dot del small r minus V dot del into W. So V dot del into small r will be equal to, again, the only way to obtain this is by expanding s. So V dot del is Vx into dou by dou x, similar to what we had done for the first case. Okay, Vy into dou by dou y, Vz into dou by dou z, and r is vector r is nothing but x I cap, because it's the position vector. It is x I cap plus y j cap plus z k cap. And when I differentiate, Vx into dou x by dou x will give us 1. So Vx into I cap. Vy into dou y by dou y is equal to 1 again. So it will give us Vy into j cap. Vz into dou z by dou z, which is equal to 1 into k cap. So it will give us Vx I cap plus Vy j cap plus Vz k cap. This is nothing but the velocity V. Now to obtain the next term, we proceed in a similar manner as in the first term in equation number 3. What's the second term say? It says that V dot del into W. We need to find out V dot del into W. We proceed in the same way as the first term, how we had done here. So what we want is V dot del into W. So here we have R dot del into V. So we proceed in the same way. Okay, so we expand this, and we will get, because you see on the here outside this is the operator, okay, and outside this we have W is a function of TR, and here V is a function of TR. So as a result, we had derivative of TR which was derivative of V with respect to TR, which is A, and then this del will replace it with gradient of TR. So we'll have the same thing over here also. So you could verify this for yourself. When you expand this out, you will find that V dot del W, so we will get a derivative of W which is equal to V itself, and this dot del, this we'll have to replace it with gradient of TR. So this is what we will get. So putting these together, okay, so we will get a V here, and this, instead of that, we'll have this one. So we will get the second term to be equal to V minus V into V dot gradient of TR. So you got another term. The first term also had a gradient TR. The second term also has got gradient of TR. Now we go to the third term. The third term is R cross del cross V. Okay, so we need to find out the third term as well. So in the third term, we'll first evaluate what is curl of V. Okay, so curl of V, again, the only way to do that is we just expand out. Okay, curl of V, we write down the expansion of curl, okay, which is basically this. And because V is a function of TR, so when we are trying to differentiate V with respect to X, Y or Z or whatever, we'll have to use the chain rule here. So dou Vz by dou Y is nothing but dou Vz by dVz by dTr into dou TR by dou Y. Same thing happens over here. Same thing will happen for the Y and the Z components also. So this is what we will get. And you can collect all these terms, and then you can show that this is nothing but the three terms. This is nothing but the acceleration. This is going to give us the Z component of A. This is going to give us the Y component of A, and then you can just put them together, and you can show that this curl of V will give us minus A cross gradient of TR. So we got one more term which has got the gradient of TR. So this gives us the third term as R cross curl of V is equal to, we have a minus sign here, minus R cross A cross gradient of TR. Now going to the last term, which is V cross curl of R. V cross curl of R. Now again the same way, R is simply, capital R is small r minus W. So we just expand this. So we have curl of R minus curl of W. Curl of R will be 0, curl of small r, because small r is the position vector with respect to the origin. So it radiates out of the origin. Okay, so it will have non-zero divergence. The position vector always has non-zero divergence, and it will have 0 curl. So curl of the position vector R, small r, will be always 0. So the first term will be 0. Second term we have curl of W. So curl of W will be equal to minus V cross gradient of TR. So how do you get this curl of W? Along similar lines as earlier when we had found out the curl of V. when we had found out the curl of V. Curl of V is equal to minus A cross gradient of TR by expanding it. Along similar lines, if we follow, we can show that curl of W is equal to minus V cross gradient of TR. This also, I'll just leave it to you for you to just try it out and verify that this is indeed the case. So curl of R is equal to V cross gradient of TR. So this gives us the last term, that is V cross curl of R is equal to V cross gradient of TR. So here again we get the gradient of TR. So there we have it. This was our gradient of R dot V. So we had 4 terms and we have obtained each of these 4 terms. I have just color coded so that it's easy to relate. So this is equal to this, this is equal to this, this is equal to this, and finally this is equal to this. So equation number 3, in equation number 3 we just need this particular equation, we just need to substitute. So this will go here, this will go here, this will go here, and this will go over here. So when we make these substitutions, so we'll get something like this. You can see here all the terms they have, except one where we have this V here, all of these terms they have gradient of TR. So now before we go further, we can observe this these 2 terms. So you see this is a triple product, right? This is a triple product, vector triple product. Okay, so one vector cross another vector cross one more vector, and for that there is already a well-known rule which is known as the back cab rule. Again, you can refer to Griffiths for the back cab rule. What it says is A cross B cross C is equal to B times A dot C minus C times A dot B. Okay, so that's why it's called as back cab rule. Again, you can just refer to Griffiths chapter 1 for this back cab rule. So we just need to apply the back cab rule on this one as well as this is the second, third and the fourth terms. So in the third term, if you observe, if you put A as R as A and small a as B and gradient of TR as C and substitute here, you will get this quantity. So because B is small a, so A into capital R dot gradient TR minus gradient TR into R dot A. So this is what we have. Substitute again, applying the back cab rule on the last term, this is what we will get. Okay, here we get V square because you see in the back cab rule what do we have inside the bracket? We have A dot B. In this case, what is A? A is small v, B is also small v. So A and B, both of them are small v. So when I take A dot B, that is small v dot v, small v, vector v dot vector v, that is nothing but your V square. So that's why I get this V square term here. So putting this back here, so we have the first term, the second term, and then this term we just replace it with this one, and this term we replace it with this. Okay, so we can see that these two will get cancelled out, and similarly this term and this term will get cancelled out, which leaves behind only 3 terms. Out of this, one term will be independent of gradient TR and the other 2 terms will contain gradient of TR. So I could just collect this gradient of TR and put these 2 inside a bracket. So that is going to give us gradient of R dot V, which is V plus R dot A minus V square into gradient of TR. Okay, so coming back to equation number 1, we were trying to find out the gradient of phi. So gradient of phi was this, and we showed that this had 2 terms. Okay, one was gradient of R dot V minus C into gradient of R. We showed that gradient of R is equal to minus C into gradient of TR, and gradient of R dot V, we showed that V is equal to V plus R dot A minus V square into gradient of TR. We did not proceed further to find out what is this gradient of TR because like I said, this term is also going to give us a gradient TR terms. So we will just collect all the gradient TR terms and then we'll proceed to find out. So now we'll find out what is this gradient of TR. Okay, so before that we just substitute all of these back here so that we can just collect all the gradient of TR terms. So substituting, so we have this going here, so we'll get V plus R dot A minus V square into gradient of TR, and then we have a minus sign here, this minus and this minus will give us a plus C square into gradient of TR. So we collect the gradient of TR terms, so we have here C square minus V square plus R dot A into gradient of TR. So we'll call this as equation number 4. Then this is equation number 4. So we'll now find out what is this gradient of TR. So we'll start with this. So minus C into gradient of TR is equal to gradient of r. Okay, we already know that. Now this gradient of r can be written as gradient of under root r dot r, because r dot r will give us r square, so r is equal to under root r dot r. So gradient will apply on this. Now when you try to work out what is gradient of r dot r, so we can use the chain rule, and using the chain rule we get 1 by, first you differentiate this function which is 1 by 2 root r dot r, then you differentiate r dot r itself. Okay. Now to find this gradient of r dot r, okay, I'll just take you back to that product rule that we had initially started our discussion on. Yes, this was that. So what we want is gradient of r dot r. Gradient of x dot y is equal to, we have these four terms. So gradient of r dot r, x and y, both of them are equal to r. So gradient of r dot r will be, so we have r dot del r. Here also we have r dot del r. So we'll have 2 into r dot del r. Then we have r cross curl r, r cross curl r. So we have 2 into r cross curl r. So we'll have, instead of 4 terms, we'll have 2 terms. When these two are equal, when both of them are equal to r, we'll have 2 terms only instead of 4. So first term will be 2 into r dot del r, and the second term will be 2 into r cross curl of r. So again we'll go back to that particular slide. Yes, so we have gradient of r dot r. So this will give us 2 terms. The first one was 2 into r dot del r, and the second one was 2 into r cross curl of r, and that 2 and this 2 will get cancelled out. So we have, again, this is going to give us 1 by r. So that's how we get this quantity. Okay, so now this term, so r dot del into r, so r dot del into r is equal to r minus v into r dot gradient of tr. How did we get this term? So again we will go back to another result, okay, which we had obtained earlier. So what we are trying to find out is r dot del into r. There was another result earlier where we had obtained v dot del into r. Okay, let me just take you back to that result. So we want to find out r dot del into r. If we go back to v dot del into r, so wherever we had that v, we just replace it with r and we'll get this result. Okay, v dot del into r, wherever we had v, we replace that v with r, we'll get again this result. So let me just take you back to that particular slide again. Yes, so this is the result. So v dot del into r. Yes, v dot del into r. So this is the result. This v I replace with r here. So we'll get a r minus r into r dot gradient tr. Okay, so we'll get this v replaced with r. So we'll get r minus r into r dot gradient of tr. So again we'll go back to that particular slide. Okay, so r dot del into r is equal to r minus v into r dot gradient of tr. Of course this v came because we had differentiated that r over there. Okay, so that's how we get, so we had differentiated w, so from there we had got this v. So r minus v into r dot gradient of tr. So you can just go back to that particular result, and just from that result you can just verify in a similar way that this is indeed going to be the case. It's a very straightforward derivation. So curl of r is equal to v cross gradient of tr. This also I think we had arrived at earlier. I think it was, let me go back. Yes, curl of r. Okay, curl of r is equal to v cross gradient of tr. Curl of r is equal to v cross gradient of tr. So we'll just pick up the result from there. Curl of r is equal to v cross gradient of tr. We just picked up the result from there. So substituting these two results back here, we'll get minus c into gradient of tr is equal to, this will get replaced with r minus v into r dot gradient of tr, and here we have, this will get replaced with r cross v cross gradient of tr. So that is going to give us this expression minus c into gradient of tr. So c into gradient of tr is this. Now look at this term. So here what we have r cross v cross gradient of tr. Again we invoke our good old back-cab rule, because this is triple product, vector triple product. So again we'll invoke the back-cab rule, and we can obtain this r cross v cross gradient of tr. Okay, a cross b cross c is equal to b into a dot c minus c into a dot b. Okay, so that will give us r cross v cross gradient of tr is equal to v into r dot gradient of tr minus gradient of tr into r dot v. Okay, so the first term was v into r dot gradient of tr, which will cancel out with this term, and what is left behind is the second term, which is gradient of tr into r dot v. So that's how we end up with this quantity. So this gives us gradient of tr. So we take this minus c on this side, so we have minus r divided by rc minus r dot v. So I mean we take this this also on this side, and then we just cross multiply, and we'll be able to simplify and write this as minus r by rc into r dot v. So this is going to give us gradient of tr. So equation number 4 was, again going back to equation number 4, gradient of phi was this entire quantity times v minus this entire thing into gradient of tr. We have now found out what is gradient of tr, which is equal to this. So we just insert this back in this equation, and that is going to give us this large expression like this. Okay, so we just add these two terms. Okay, subtract from v, we subtract this term. Okay, so we have rc minus r dot v into v minus this entire thing into r, and this rc minus r dot v, I take it outside, so we'll get rc minus r dot v. Already there is a square, so this is going to be a cube. So we call this equation number 6. Okay, so we have got this gradient of phi. Now from the vector Liénard-Wiechert potential, A is equal to r comma t, which is equal to a of r comma t, which is equal to v by c square into phi, right? And phi is equal to this quantity. So we can similarly we can obtain the dou a by dou t. We have to differentiate this with respect to time, and when you differentiate this with respect to time, you have to remember we have 1 by c square dou by dou t of v into phi. So we have to apply the product rule here. So apply the product rule. Okay, so we'll have a time derivative dou phi by dou t. When you apply the product rule, so we'll have two terms. One term contains phi, other term will contain dou phi by dou t. So differentiate this phi. Okay, you'll get dou phi by dou t, and then that phi again we'll take it from here and substitute both back in dou a by dou t and simplify this, and then we will get this expression. So again this is along similarly just substituting and doing some manipulation and obtaining the result. So this again I'm not going to do over here. I'll just leave it to you as an exercise. You can try it out. It is pretty straightforward itself. So this gives us gradient of phi is equal to this, and dou a by dou t equals to this. So equation number 6 and 7. Now these two equations, if you see, they are really ugly looking, because you see it's too big and then very clumsy, right, these two equations. So in order to simplify the expression somewhat, we will introduce a new quantity, a new vector, which we call as u. U is simply equal to c r cap minus v. Physically, this is how we can understand. What is r cap? R cap is the unit vector which points from the retarded source position to field position. Field position is that position where I'm trying to find out the field. Source position is where we have the source charge. So this is the retarded position. At the retarded position, we have a unit vector which points from the retarded position till the field position. So this is your r cap. And then this you multiply with c. Okay, r cap you multiply with c. Why we multiply with c? Because the electromagnetic information is traveling along this line at a speed c. Okay, so this is going to give us the speed, the velocity with which the electromagnetic information is traveling towards the field position. Okay, so this quantity c into r cap will be this vector c r cap. Okay, and v is the velocity of the particle. So c r cap minus v will be this particular vector. So this is the vector which gives us the velocity with which the information is flowing from the retarded position to the field position, and v is the velocity with which the source itself is moving. So we introduce this new quantity u, and you can note here that if I take the dot product, if I take r dot u, if I take r dot u, it will be r dot c r cap minus v. So c is anyway constant, so we have r dot u is equal to c r dot r cap, okay, minus r dot v. R dot r cap, okay, r dot r cap will simply give us the modulus r. Okay, so the first term will become rc and the second term will become r dot v. Rc minus, so r dot u will give us rc minus r dot v, rc minus r dot v. So this quantity that we have is nothing but r dot u. So we can combine, we can these two equations, we can just combine them together to obtain the electric field, okay, in this way, and we can utilize the definition u to rewrite the combined expression in this form. So we'll have this quantity here will become r dot u, and also the other quantities, the terms that are there inside, those also can be simplified, and we can write it in a much more manageable form of the electric field, which is given as equation number 8. Okay, so now we have just found out the electric field. So now next thing is that we need to find out is the magnetic field, so curl of A. Now A is equal to V by C square into phi from the Liénard-Wiechert potentials. So we know that A is equal to V by C square into phi. So therefore curl of A will be simply equal to 1 by C square curl of V into phi, curl of V into phi. Now curl of V into phi, again we have to use the product rule. So we have phi into curl of V minus V into V cross gradient of phi. So this is the product rule whenever you're trying to find out the curl of a product of a scalar function and a vector function. So this is what we have. So over here in this expression we have already found out what is this phi, right? We have already found out what is this phi. Where is it? Yeah, okay, that was the Liénard-Wiechert potentials. We already know what is phi, right? The Liénard-Wiechert potential, we already know what is phi. We also know what is gradient of phi here. We already know what is gradient of phi. So this is gradient of phi. So we already know what is phi, we already know what is gradient of phi, and we already know what is curl of V, which is minus A cross gradient of TR. We already know which is curl of V, which we have already calculated, okay, in when we are trying to find out R dot the first term, right, gradient of R dot V. Yeah, when we are trying to find out that term, there were 4 terms, and in that process we had found out what is curl of V. Curl of V is equal to minus A cross gradient of TR. So we insert these in this expression, and we use the definition of U, and that is going to give us curl of A to be equal to this. So B is equal to curl of A. Curl of A is equal to this quantity, and the electric field we have already obtained it to be like this. So we can use these to show, okay, B is equal to this entire quantity and the electric field is this. So from here we can show, by doing a little bit of manipulation, we can show that B can be written as 1 by C into R cross this electric field. So if I take R cap cross this electric field, that is going to give me this same expression. Okay, of course you have to multiply with 1 by C. So that is nothing but a magnetic field. So you can find out the magnetic field in terms of the electric field as well. So finally, these are the fields due to the accelerated point charge. This is what we are trying to find out. So E is this and B is this. So a few observations. The first observation is that of course B due to a point charge is always perpendicular, because B is equal to R cap cross E. So B is perpendicular to E, and B is also perpendicular to R cap, because R cap is the vector from the retarded point to the source point. Okay, so R cap is the unit vector which points from the retarded point to the source point. So B is always perpendicular to both of these vectors. And also one more thing is R dot U is of the order of R, okay, because U, what is U? U is simply C R cap minus V. U is C R cap minus V. So R dot U will be of the same order as R. Okay, so if r dot u is of the same order as r, so in the electric field, if you see, we have two terms, the first term and the second term. The first term, it will vary as 1 by r square. You can see how that happens. What is the first term? The r, we just collect them. So this entire thing, that will be the first term. Of course, q by 4 pi epsilon naught, that's anyway constant. So we'll just combine this. Consider this. R dot u varies as r. So we have a r already in the numerator. And r dot u, this varies as r. So in the denominator, we'll have r cube. So r by r cube, that will give us 1 by r square. So it means the first term, it varies as 1 by r square. And the second term, it varies as 1 by r. You can see how. So we have r into, there is another r here, and here we have r cube. So r square in the numerator, r cube in the denominator. So that is going to give us 1 by r. So first term varies as 1 by r square. Second term varies as 1 by r. So that's why the first term is known as the velocity field and the second term is known as the acceleration field, simply because the first term, it contains velocity and the second term, it contains acceleration because of this region. So first term contains, the velocity is contained only in the first term and acceleration is contained only in the second term. So the velocity field is that field which varies as 1 by r square, and the acceleration field is that field which varies as 1 by r. Also, you can try it out for yourself. If you consider a charge which is not moving, a completely static charge, then what do you expect? If you consider a completely static charge, we expect that this should come down to the Coulomb's law, and that's what happens. Because if this charge is stationary, that means its velocity is 0 and its acceleration is 0. V is 0 and A is 0. A is 0 means the second term will become 0. V is 0, so in the first term we'll only have c square into u. Okay, when V is 0 and A is 0, u will simply become c into r cap, because u is defined as c r cap minus v. V is 0, so u will simply become c into r cap. So we can simplify this. Okay, we can simplify this and we'll find out that you can try it out for yourself. When you put v equal to 0 and a equal to 0, you'll find that the second term will vanish, of course, and the first term will collapse to this particular term, and this we can immediately recognize. This is kq by r square. This is nothing but the familiar electrostatic field that we got from the Coulomb's law, and for this reason the first term is also known as a generalized Coulomb field. Okay, so for this reason it is also known as a generalized Coulomb field, because it boils down to the Coulomb field in case of a stationary charge. And the second charge, it varies because it varies as 1 by r. We know that 1 by r, it dies down much slower compared to 1 by r square. 1 by r square dies down very fast, 1 by r dies down much slower. So at the long range, it is the second term that is going to contribute. Okay, in the long range, very far away from the sources, it is the second term that is going to actually contribute to the field. Okay, and this second term is what contributes to the radiation of the charge. Okay, and that's why we say that radiation, electromagnetic radiation is due to accelerated charges. Stationary charges, they never produce electromagnetic radiation. It's only the accelerated charges which produce electromagnetic radiation. Okay, because at the long distance, when you're far away from the sources, it is the second term that is going to dominate, and that is going to give us the radiation. That's why the second term is also known as the radiation field. So again, now we have finally we have electric field and magnetic field. So once we have the electric and field, now we are in a position to ultimately calculate what will be the force between charges. So let's say I have a source charge Q and I have a test charge capital Q, which is placed over here. The source charge is moving at a velocity v and the test charge is moving at a velocity capital V. Then this test charge is going to experience a force, an electromagnetic force, due to this source charge. Okay, let's say that the electromagnetic force is F. Then what will be this electromagnetic force? Very simple. It will be nothing but the Coulomb, the Lorentz force law, which is F equals Q into E plus V cross B. All we have to do now is take this E and take this V, substitute over here, simplify this, and we will get the force, the mutual force between a pair of charges, the mutual electromagnetic force between any pair of charges. and together, instead of one charge, let's say I'm having a collection of charges or a distribution of charges, then we can just use the superposition principle to find out what is the force acting on this particular charge. So in effect, essentially we can actually claim that the entire electromagnetism in electrodynamics is actually contained, the information that is there in entire electrodynamics, it is actually contained within this expression itself. So this ends this particular discussion on dynamic charges. I will actually include some of these steps involved in the derivation. I have skipped in this because, and I have also, but I have provided you hints as to how we can obtain those. So I'll just leave those as questions in an assignment. So I'll leave it to you as an assignment, and I'll upload them along with the slides on your Google Classroom. Please go through these slides and solve the problems, and in case of any queries, don't hesitate to contact me. So with this we come to the end of this lesson. Thank you.